Now let's solve this question number 3. It says that experiment with 3 hyperparameters included in the lecture and write a short summary of what we have learned. So let's see, what are the hyperparameters first of all. So hyperparameters, some of the example you can clearly see right here. They can be tuned, they can be changed in order to make your model more that is accurate and so on. So in machine learning model, which is the definition of a mathematical formula with the number of parameters that are needed to be learned from the data. So basically definition is that, and that is done through some of the process that is called as a model training. Also, in other words, training a model with existing data, we are able to fit a model. There is another kind of parameter which are not able to learn directly regular during the training process, which is expressed as a higher level properties of any other model, and that is because of its complexity or how fast it should learn, something like that. And these parameters are called hyperparameter, and they are usually fixed before the actual training process begins. So this process, like we can remember, if you see what is the difference between parameter and hyperparameter. So in the neural network, if you remember, we have something that is weight. So weight is connected, this connection between one neuron with another is a weight, and they are called the parameters. Now they are updated during the process, during the training process only. Now, because in the training process there is a back propagation. If you remember, there is a back propagation which is going to update this weight and reduce the loss of our model. But if you want to just change the model in a way that it should be done before the training process, then that should be your hyperparameter. Some of the example of the hyperparameter is given here. Number of the leaves of the descent tree. That means this is nothing but like how many hidden layers there should be. Like how many hidden layer we should choose, and you should choose a hidden layer in a such way that you need to increase a hidden layer if your data is complex. Like if your data is audio or video or images, we use huge number of that is hidden layers or hidden layers unit or number of neurons. So basically you can consider it as number of neurons. As your data gets complex, you can increase the depth of the hidden layer or the size of the hidden layer. So this way we can change the hyperparameters. Second is a learning rate. If you just see this learning rate, we can have different approach for assigning this learning rate. We can have constant learning rate if you want, constant, which should be used for the entire model, or you can also use adaptive learning. If you want adaptive learning rate, then you can also use adaptive learning rate. And similarly, hidden layer, we can change the hidden layer, number of cluster in a K-means clustering, or number of latent factor in the matrix factorization. These are the hyperparameters. So first experiment, let's go with the first experiment. So what changes did we do in the first experiment? So activation is ReLU. We didn't change the size also, which didn't change the solver also. We only changed the batch size. So batch size was 32 at first. Now we change it to the auto, and we saw our output when it was converging. We predicted, we just evaluate our model. We just saw what was the accuracy and confusion matrix and everything. So we saw over here, and you can also see the accuracy over here where this will converge, how much loss is converged. You can see different iteration going on over here, and this way we just printed the confusion matrix classification report also. Now second experiment with the hyperparameter. What we did here, we changed the solver. If you remember, it was Adam at first. Now we use here SGD, which refers to stochastic gradient descent. Now we are using stochastic gradient descent. We are also using this adaptive as our learning rate. We are not using now that is constant. We are using adaptive. So what is adaptive and what is a constant? So adaptive means, basically adaptive refers that your change in the learning rate should be small at the beginning, and as the model goes, like as the model will try to converge to the minimum point, your learning rate should be smaller and smaller. So that means at first our learning rate will be huge. That means the gradient will be huge. The gradient will be huge. That means it will just work just faster. And as the point of convergence is approached by the gradient, your learning rate should be smaller. It should be smaller and smaller. What is the advantage of it? The advantage is basically we never will overshoot. There is low chance of overshooting the global optimum. our model can converge at the particular point perfectly using this adaptive approach. So this is the way. So next, you can also see we predicted and we did the third experiment where we use the ADAM again, back to the ADAM, not SGD, it was SGD or ADAM. So we use ADAM again, which is an optimizer. We use batch size as an auto, and ReLU you can also use sigmoid if you want, but sigmoid doesn't do good in the multi-class classification. We can use ReLU, and similarly we increase the size also. See here, there was 300 at the beginning, now we changed to the 400. So number of neurons also increased. And we use now learning rate as inverse scaling. So this is the inverse scaling learning rate. And we just plotted everything over here. We saw the confusion matrix, how it performed and so on. Now all the description about this experiment is given over here. Now we can just see the learning rate. So at first we just had the learning rate as constant for the experiment number 1. So that means learning rate was constant for entire program, which was defined by this learning underscore rate underscore init. We had given something that is the value of this is 0.001. So this value was common for entire, this was not going to change for entire program when the learning rate was constant. And in the second experiment we did learning rate as adaptive. So what is the adaptive? So adaptive means the experiment second, in that case learning rate was constant to the learning rate in it as long as the training loss keep decreasing. So that was the reason we have this training loss. If you remember the training loss, whenever the training loss was going to decrease, because loss is not preferable in our program. Loss is nothing but an error. So loss is same as saying error, and we don't want error in our program. So we need to decrease this loss. So decreasing in loss, whenever the decrease is happening in the loss, then we use the same constant learning rate in it. But whenever the loss is not decreasing, we are going to make a adaptation in the learning rate. So that was our learning rate, and that is used with this solver, that is stochastic gradient descent. Now at last the learning rate was inverse scaling, which says that the learning rate should gradually decrease. So at first it will be a high learning rate, and after that it should decrease. It should decrease by some amount that is given over here. At each time step t, the learning rate should decrease gradually, and this is using this power t method, which formula is given right here. Using this formula we are going to adapt the learning rate. The learning rate is going to decrease at each time step. So that is all the difference about the learning rate. If you put the constant, it is going to be the constant, which will be some value. If you put the learning rate as an adaptive, then until and unless loss is decreasing, it will be constant. But whenever the loss is, the learning rate will be stopping there. That is an adaptive. Whenever the loss is not going to change, if the loss is basically, let's say after going at some point, the loss again increased. So at that point there will be adaptive. So adaptive works better in that case. And after that there is inverse scaling, which just decrease our learning rate constantly, and that is done by gradual process. With the help of this time step, we are going to use this power in order to check for that time step and gradually decrease our learning rate. So this is all the hyperparameters that we experiment with. You can experiment, you can put different activation function that we have learned, like you can put sigmoid, you can put leaky ReLU, you can put 10th if you want, and this activation can be used in order to see and check whether we will be able to get high accuracy or high model and lower loss or not in our program. Similarly, these are called the hyperparameters. You can tune it before the training process so that we will get better accuracy. This is all about hyperparameters, and this is all about multi-layer perceptron model. This code will be available on the resource section. Make sure you take a reference from it, and just go with one by one the description. These description are very important. I have written especially for the student, which will be available after the lecture is also finished. You can just reference this back and just learn from this a little bit more after even the course is finished, or after even the lecture is finished. So that is all in this code session of multi-layer perceptron. See you in the next one.